Hello, my name is Patrick, and today I will be discussing lab 4, which is magnetic braking with Faraday. So here's the outline of my lab. I will start with the introduction and go all over the additional questions. So in this lab, we will explore the Faraday's law and the interaction between a falling magnet and a tube of aluminium foil. We will then use a magnet and aluminium foil to observe the magnetic field and flux in real life, and then create a model to simulate a bar magnet being dropped in a conductive tube. And some of our results in the experimental lab is that we found that it took for the magnet 1.2 seconds to fall, and from the computational model it only took 1.7 seconds to fall. Some of the principles that we will use is the Biot-Savart law and the Faraday's law and Lenz's law, which will help us find the voltage correlated with time derivative of flux and the induced electric current, which creates magnetic field opposing the changes. Using Newton's second law to update the position and velocity of the magnet, and Newton's third law to find the force of the following magnet by the tube rings. Some of the material that we will use in the lab is a smartphone, a bar magnet, a roll of aluminium foil, and a meter stick. Using the material, we will record the physical properties of aluminium foil cylinder, then drop magnet down, starting from North Pole, and then measure the time it takes to each button and average the 5 trials. And we found out that the average time is 1.206 seconds. So what happens to the magnet? It will fall through the tube and exit vertically. It will also experience some resistance. And how does this compare to a magnet falling in free space? Well, I found out that it will take longer to fall through the foil than the free space. So for the computational model, we first set some constants such as mu0 over 4pi, and then we set the geometry of the tube with a length of 0.3 meter and width of 0.025 meter. So in large, we checked if the magnet is in the tube, then we iterate across the rings to find the net magnetic force on the magnet. We find the magnet's acceleration and we updated its position accordingly. And in the end, we plot the magnet's position and velocity versus time. So those are the results that we find, with the time of 1.754 seconds for the magnet to fall through the tube. The color of the tubes indicate the current flowing in the ring. Red indicates clockwise and blue indicates counterclockwise, according to Lenz's law. If you flip the magnet, nothing will happen, but the current then slip and flow in the other direction that we have been seeing. The total time in real life and the one we computed are different. The one we computed was longer than the one in real life. And in order to make the model more accurate, we could split the ring into more rings and take into account air resistance. The shape of the velocity versus time tells us that the force acting on the bar magnet will become 0. Now for the additional questions. What if the resistivity of the conductor were reduced as close as possible to 0? While the magnetic force and current will grow in magnitude, the current and resistance are inversely proportional. And we know that the magnet will fall slowly. So what if holes or slots were cut into the tubes? How could this affect the ring currents in the model? Well, the cylinder will contain fewer hole rings and weaker magnetic force on the magnet. And in this case, the magnet will fall faster.